Hey everyone, it's me, Mr. Younger. I have an example to show you guys today on a center of mass calculation for a discrete number of objects. In this case, we actually have three small spheres that are going to be embedded in some sense on a triangular plate. And initially, we're going to calculate the center of mass, ignoring this triangular plate, which is markedly lighter than the individual masses. And in the second part, we're going to calculate it with the triangular plate and see how much of a difference it makes as well. So we can get started. Let's go ahead and open up my iPad and share the screen with you guys. All right, so you can see the problem typed out here as well as a diagram to show exactly what I'm talking about. It says three small spherically symmetric spheres are attached to a light plexiglass triangular plate whose mass is 150 grams, such that the center of mass of each is at a vertex of the triangular plate. The triangular plate is a right triangle whose sides are 30.0 centimeters and 40.0 centimeters. The 1.00 kilogram sphere is centered where the 30 centimeter side meets the hypotenuse. The 2.50 kilogram sphere is at the vertex of the 90-degree angle, and the 1.25 kilograms sphere is centered on the vertex where the 40 centimeter side meets the hypotenuse. In part A, they want us to find where is the center of mass for the three masses, ignoring the plexiglass plate, and it tells you, of course, to see the figure. In part B, it wants you to assume the center of the mass of the triangular plate is 10 centimeters to the left of the 40 centimeter side and 13.3 centimeters above the above the 30 centimeter side. And they want us to determine the center of mass in this case when we're counting all four parts. So we've got the drawing set up here. I've typed out and written out a lot of the solution already. I'm trying to speed up the process so you don't just have to, you know, waste time watching me write. So here is the solution beginning. Obviously, the solution, I normally state exactly what variables we've been given. I assign the particular numbers that we've been given to particular symbols so that we can know what equations they apply to, and we usually supply the equations that we're going to be using. In this case, the diagram pretty much shows everything but the mass and the center of mass of the triangular plate. That's the only thing that's not really shown on here, but we'll pull that in as needed. But we do need the formulas. So the formula for the center of mass, as far as the x part or the abscissa portion of the point, is m1 times x1 plus m2 times x2 plus dot 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 for however many objects that you have. And then you're going to divide all that by m1 plus m2 plus dot 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 for however many objects you have. Similarly, the y center of mass, in this case, it's the ordinate of the center of mass. That is m1 y1 plus m2 y2 plus dot dot dot. All of that divided by the sum of the individual masses m1 plus m2 plus m3 for however many you have. Again, in the event that the M1, M2, M3, however many you have, if they aren't individual point particles, then it's just important that you make sure you find the center of mass of each of them. And when it says X1, for instance, in the formula, that means the abscissa or the X portion of the point where the center of mass for particle one is, or for object one. Similarly, X2 is the abscissa for the center of mass for particle M2 or for object M2, and similarly for Y1 and Y2 and so on and so forth. So according to the formulas, we should choose a coordinate system. To that end, I would choose the origin at the leftmost vertex and the x-axis pointing to the right and parallel to the 30 centimeter side. So what I'm saying here is I'm going to put the origin right here, and then the x-axis is going to extend this way. And I didn't say it, but I will extend the y-axis this way. You're completely free to choose the coordinate system any way you want. Just once you choose it, you sort of want to stick to that. And of course, by showing it on the work, then I know exactly what you're doing and I can see from your calculations. So to this end, we now have the ability to put the coordinate system in. I'm going to flip to another page where the coordinate system has been drawn in already. You can see it there. So we can see, for instance, that the x coordinate of M1 is just 0. The x coordinate of M2 is 0.300 meters, and the x-coordinate of M3 is also 0.300 meters. Similarly, y1 is 0, y2 is 0, and y3 is 40 or 0.400 meters. So using that information, we can begin x center of mass should be equal to, and I'm not going to write the units, at least not in the numerator because they take up so much space, but just remember one's a kilogram and the other one's meters. I could use centimeters and I could use grams. It wouldn't matter as long as I use the same units top and bottom for mass. Then they'll all cancel out and everything will work out fine. But M1 X1 will be 1.00 kilograms times the x coordinate, also called the abscissa, in this case is 0.00. Okay, that would be in meters. And then plus the next one, which is 2.50 kilograms. And that has an abscissa of 0.300 meters. And then the final one is mass 3, which is 1.25 kilograms, and that is also at 0.300 meters. Then we're going to divide all this by the sum of the masses. That'd be 1.00 kilograms plus 2.50 kilograms plus 1.25 kilograms. Now, I need to pay a little bit of attention because we are doing addition in the numerator, so I got to pay a little bit of attention to the individual calculations for each term in the numerator so that I can figure out how many decimal places are sig figs. Again, if your instructor's not one that cares about sig figs like me, then don't worry too much about it. But just in case you aren't, I do try to be pedantic on these solutions. So I'm going to take the 1 times 0, that's obviously 0, so I don't have anything to concern myself with there. But when I take the 2.50 times 0.300, that's 3 sig figs, and the answer is 0.75. 3 sig figs suggests that the answer is 0.750, so that the ones place, the tenths place, the hundredths place, and the thousandths place are all significant for that middle term. And then when I multiply 1.25 times 0.3, I get again, or in this case, I get 0.375, and that's 3 sig figs. So that means all 3 of the digits after the decimal are in fact significant. So I'm going to take the 0.375 and I'm going to add that to the 0.75 and add that to the 0, and all of that gives me 1.125. Now that is actually good to 3 decimal places, so I could actually put a 00 here to have 2 extras, and that would be in kilograms times meters. And now I'm going to take the 1 or the bottom and add those up. So that's 1 plus 2.5 plus 1.25. And again, just making sure I didn't make any careless mistakes, I went ahead and put that in the calculator, and that gave me 4.75 kilograms. So you can see, as advertised, the kilogram in the numerator will cancel out with the kilogram in the denominator. And you can also see that in this case, I have 4 sig figs divided by 3 sig figs. You could put a 0 after the 5, but that's not a sig fig either. So if I take the 1.125 and divide it by 4.75, I should get 3 sig figs, and that gives me, oops, wrong color. That gives me 0.236. There's my 3 sig figs. And then 2 extra or 2 extra digits would be 6, 8. And that unit is in meters, and I'll underline that. So that's my X center of mass for this arrangement. And I'll go ahead and box that off. Now I can do the same calculation for the Y center of mass using the same, the Y values that I already mentioned to you. Here we go. YCM is going to be equal to 1.00 times, in this case, the Y is also 0.00 plus 2.50 kilograms times 0.00 meters is again Y. And then finally, we got one that has a Y that's not equal to 0, and that is the 1.25 kilograms times 0.400 meters. All of that will be divided by the sum of the masses, which we already know, but just to write it all down, plus 1.25 kilograms. So in this case, 1.25 times 0.400 gives me 3 sig figs. So this is 0.500 kilograms meters for the numerator. And then for the denominator, of course, it's 4.75 kilograms. Again, the kilograms can cancel out. And we get 0.5 divided by 4.75. That again gives me 3 sig figs divided by 3 sig figs. So I get Y center of mass is equal to, I complete that, it's 0.105, and then 2 extra digit would be 26 meters. And that is YCM. And I've obviously run a little bit out of room in that space. So I'm just drawing it like this. And that's the X center of mass and the Y center of mass for this particular arrangement. Now, if we wish to calculate the other part, which is the same problem, only this time we're including the mass and the center of mass of the triangular plate, then we can do as follows. It would probably be helpful for me to have this drawing here as well, but anyways, I think I can still do it without it, just out of memory. So the part B, XCM, is going to be 1.00 kilograms times 0.00 meters plus 2.50 kilograms times 0.300 meters plus 1.12, or excuse me, 1.25. Let's go ahead and give ourselves a little bit more clearance there. 1.25 kilograms for that one times 0.300. Now we also have the mass of the triangular plate, which if we look back at the question, that was 0.1500 kilograms. So this would be 0.1500. And then its position, they said, would be 10 centimeters to the left of the 40 centimeter side. So that corresponds to an x equals 0.20. So 0.200. And then all of this will be divided by, we already knew the original mass was 4.75 kilograms, but now we're adding the additional 0.1500 kilograms. So in this case, we're going to get 0 times 1, that's 0. I'm going to get 2.5 times 2.50 times 0.300. And that gives me the 0.75. So that's the 3 significant, or the 3 decimal places. And then I'm going to take plus 1.25 times 0.300. And that one, of course, gives us the 3 decimal places as well. So the top, before I add in the actual plexiglass, is 1.125 kilograms times meters. Now I'm going to add in, just so we can see what's going on, I'm going to add in the 0.15 times 0.200. and this gives me 0.030. That actually was to 4 sig figs times 3 sig figs, so I should have 3 sig figs. The first digit came in the tenths, or excuse me, in the hundredths place, so it should be good to not the thousandth, but the 10,000th, which would be, as shown here, kilograms times meter. And then all of that will be divided by 4.75 plus 0.15. So this would be 4.90 kilograms. So again, we can see that the kilograms cancel out, but what is our actual result? 1.125 plus 0.03 is 1.128. Excuse me, 1.125 plus 0.03. Oh, sorry, is 1.155. So I'll go ahead and write that. 1.155 meters, and all of those are sig figs, and all that's divided by 4.90, and that gives me 0.235, and then two extra non-significant digits would be 71 meters. So if we compare what we got to the first time, 0.235 or 0.236 versus the first time was 0.237. So really not a huge difference. Now we're going to do the same thing for the Y center of mass, but I'm going to go ahead and box this off first. So this is X center of mass. And I'm going to say with triangular plate. Okay. So that's our answer to part B, X center of mass. Now, part B, Y center of mass, again, is going to be the same thing that we had on the top. It's those same numbers. I could write them out again. It would be 1.00 times 0.00 plus 2.50 kilograms times 0.00. You remember we're doing the y coordinate, and neither the M1 or M2 have a y coordinate. They have a y coordinates, but it's actually 0 because they're actually on the x-axis. But the M3 is actually up at 0.4. So that M3 is 1.25 kilograms, and that is up at 0.400. Yes, that looks fine. And now I have to also add the plexiglass, and the plexiglass has a mass of 0.1500 kilograms, and its location is actually 13.3 centimeters up, so that'd be 0.133 meters up. All of this is going to be divided by 4.75 kilograms that we know we got from the original three parts, plus 0.1500 kilograms. That's basically what it should be. Now I can do the math. It's 1.25 times 0.4. Now that's 3 sig figs times 3 sig figs, and that gives me 0.500, so that's good to the thousandths place. And now I'm going to take 0.1500 times 0.133. That's 4 sig figs times 3 sig figs. When I multiply those, I get 3 sig figs, and that means that should be up down to the 10,000ths place. So I get 0.500 with a line under it for the first half, or for the first three, plus 0.01995 kilograms times meters. That's just the part for the plexiglass, and you can see that the sig figs go all the way to the fourth decimal place in this case. Actually, it should be to the tenths under, yeah, fourth decimal place. There you go. The 5 is not. And then the 4.75 plus 0.15, 4.75 plus 0.15 should give me 4.90 kilograms. Again, the kilograms cancel out with the kilograms here and here, and I'm just left with 0.5 plus 0.01995. And again, that gives me to the third decimal place because we're only good to the third decimal places. That means I have 3 sig figs. And now I got to divide that by 4.90. And that also has 3 sig figs. And those 3 sig figs are 0.106 space 11 meter. So the Y center of mass, or actually I should write it this way. I'll just put the number down here. 0.10611 meters equals YCM with triangular plate. So I can box all this off, and we can see in this case we got 0.106 or 10.6 centimeters to the right of the coordinate, or excuse me, up from the y-axis, so 0.106 compared to what we had the first time, which was 0.105. So it actually did move a difference of one sig or one digit in the last sig fig. So there, it actually was enough of an approximation to exclude it unless you needed 2 decimal place or 3 decimal place precision in meters. If you did, then yeah, you need to go ahead and include it. But if you only needed 2 decimal places in meters for the X center mass and Y center mass, then clearly you could have ignored it. So anyways, I hope that's a good, useful example of how to use the center of mass calculations, how to perform them in 2 dimensions. I guess that'll be it. I'll stop sharing my screen and say bye-bye. Thanks again.